Hey there, and welcome. Have you ever thought about chemistry as, well, as a really precise form of cooking? Because at its heart, that's what it is. It's all about recipes. You take some ingredients, mix them together, and you get something totally new. Today, we're going to dive into how chemists write those recipes using the universal language of chemical equations.
And we're not just talking about any old recipes here. We're talking about recipes that are powerful enough to launch people into space. So let's kick things off with the incredible example of solid rocket fuel.
You know, the key phrase here is precisely measured amounts. If you get that recipe even a little bit wrong, the results could be, well, catastrophic. This isn't like adding a little extra garlic to your pasta sauce. Nope. This is about generating a massive, controlled force to literally escape Earth's gravity. The stakes are just incredibly high.
So that leads us to the big question, right? How in the world do you write down a recipe that has to be that perfect? How do you keep track of every single tiny particle when you're dealing with such a massive reaction? Well, the answer is in this universal language, this simple, really elegant structure of a chemical equation.
To really understand the recipe, we first have to know how to read it. So let's break down the anatomy of a chemical equation, piece by piece. Think of it like learning the language of the universe's kitchen. So every chemical equation has two sides, super simple. On the left, you've got your reactants. These are your ingredients, the stuff you start with. Then, on the right side, you have the products. That's your finished dish, the new stuff you create after the reaction goes down. It's a really straightforward setup. Ingredients on the left, what you made on the right.
And splitting those two sides is the arrow. The arrow is the action. It's the chemical change itself. You can read it out loud as yields or becomes. It's basically the instruction in the recipe, you know? The mix, heat, bake, combine. It's the moment of transformation.
Okay, but how do we know how much of everything to use? That's where coefficients come in. These are the big numbers you see in front of each chemical formula. They're telling you the quantity, how many molecules of each ingredient you need, and how many you're going to get of each final product. They're basically the 2 cups or the 1 tablespoon of our chemical recipe.
So why is all this counting so incredibly important? Well, it's because chemistry, and really the entire universe, operates under one unbreakable golden rule. And this rule is the whole reason we have to balance equations in the first place.
And this is it, the law of conservation of matter. It's a fundamental principle, and it basically says you can't just make atoms appear out of thin air, and they don't just disappear into nothing. All you can do is rearrange them into new combinations. So whatever atoms you put into the reaction, you have to get the exact same number of each type of atom out at the end. No exceptions.
And this is just a beautiful illustration of a perfectly balanced equation. This is what happens when you burn methane. Just look at the table. We start with 1 carbon atom on the left, we end with 1 on the right. Check. We start with 4 hydrogen atoms, we end with 4. Check. And we start with 4 oxygen atoms, and we end with 4. Perfect. Everything is accounted for, the books are balanced.
Okay, so now we know why we have to balance equations. But how do we actually, do it? It's really a process of careful counting and a bit of trial and error. It's kind of like solving a little puzzle. Let's walk through one together. We're going to start with a really simple but super important reaction, the decomposition of water. As it's written right now, this equation is totally unbalanced. It's actually breaking the law of conservation of matter, so let's fix it.
All right, first step is always to take inventory. We count up the atoms on both sides. So we've got 2 hydrogens on the left and 2 on the right. Hey, so far so good. But look at the oxygen. We have only 1 oxygen atom on the left, but there are 2 on the right. Uh-oh, that's a problem, or recipe is wrong.
So to get 2 oxygen atoms on the left side, our only real move here is to change the coefficient. Remember, we absolutely can't touch that little 2 in H2O. That would change it from water into something completely different. So let's try putting a big 2 in front of the H2O. That gives us 2 water molecules to start with. Okay, let's recount. We did it! We fixed our oxygen problem. We have 2 on the left and 2 on the right. Awesome! But in fixing that, we've kind of created a new problem. Now we have 4 hydrogen atoms on the left side, but we still only have 2 on the right. So we're not quite done yet.
But this last step is actually pretty easy. To get 4 hydrogen atoms over on the product side, all we need to do is put a coefficient of 2 in front of the H2. That gives us 2 molecules of hydrogen gas. So let's do our final count.
And there we have it, 4 hydrogens on both sides and 2 oxygens on both sides. The equation is now perfectly, beautifully balanced. This is the correct recipe.
2 molecules of water will yield 2 molecules of hydrogen gas and 1 molecule of oxygen gas. The universe is back in harmony.
Now, as you get into more complicated equations, there are a few tips and tricks that chemists use to make this whole balancing process a little bit smoother. Let's go over a couple key rules of the road.
First, a really important rule of thumb. Always aim for the simplest whole number ratio. So if you end up with coefficients like 2, 4, and 6, you need to simplify them down to 1, 2, and 3. Second, and this is maybe the most important rule of all, never change the little subscript numbers in a formula. Changing H2O to H2O2 doesn't balance your equation. It changes your ingredient from water to hydrogen peroxide. And finally, here's a little pro tip. If you get stuck, you can actually use a fraction temporarily to get things to balance, just as long as you remember to multiply the entire equation by a whole number afterward to get rid of it.
So far, we've been looking at the big picture. But for reactions that happen in water, there's often a lot more going on right under the surface. We can actually write equations with different levels of detail to find out what's really reacting.
So take a look at this. This is called a molecular equation. It shows the complete neutral compounds that are involved in the reaction. That little AQ just means aqueous, or that it's dissolved in water. This gives us the overall recipe, sure, but it's kind of hiding an important detail about what's actually going on in the water.
Okay, now here's what's really happening. This is the complete ionic equation. See, because those aqueous compounds are dissolved, they break apart into their individual ions, and they're all just floating around. But look closely. See how the calcium ion on the left is exactly the same as the one on the right? Same thing for the nitrate ions. They aren't actually part of the chemical change at all. We call these spectator ions. They're just watching the action from the sidelines.
So if we just remove those spectators, we're left with this, the net ionic equation. This is the heart of the reaction. This shows us only the particles that are actually participating in the chemical change. In this case, the silver and chloride ions coming together to form solid silver chloride. This is the real action, with all the distractions cleared away. You know, from the fuel in a rocket to the fizz in your soda, chemical reactions are happening all around us, all the time. And they all follow these same fundamental rules of balancing. So I guess the final question is, now that you can read and write the universe's recipes, what reaction in your world, whether it's baking a cake, lighting a match, or the battery powering your phone, what would you want to explore first? Thanks for joining me.